Day of this unit, we said there were 4 properties of waves that are exhibited by EMR. One of those properties is refraction. Refraction is the bending of a wave. That's exhibited by EMR. Therefore, according to refraction, EMR must be a wave. The second one was diffraction. We defined diffraction in Physics 20 and on the first day of this unit as the spreading out of a wave around a barrier or through an opening. This is not the same as refraction. Refraction is the bending. As it changes speed, it changes direction when it goes from one medium to another. With diffraction, we don't have to change media. We don't have to go from one material to another. We just have to send the wave through an opening or around a barrier. You can see in this photograph here that we have water waves in this case, not light, but light exhibits the same properties. Water waves go through this little opening and then spreads out as it goes through that opening. That's diffraction. It's a property of waves. That property of waves is exhibited by EMR, and therefore EMR must be a wave. Now, if we had 2 openings here, opening number 1 right here, but we had another opening right here, then we would get diffraction around both openings. Now, if you get diffraction around both of these openings, then at some point you might get some overlap of the waves. As the waves spread out from opening number 1 and the waves spread out from opening number 2, wave number 1 overlaps with wave number 2. When that happens, we get a phenomenon called interference, right? Which is another property of waves that is exhibited by EMR. Here's a photo that shows interference taking place with water waves. Here we have a source right here. Let's say water waves are going through an opening at this point. Water waves are going through an opening at this point as well. And that's causing water waves to go like this. Those water waves are diffracting from opening number 1, they're diffracting from opening number 2, and then they're overlapping or interfering. When the crest of one wave overlaps with the crest of another, or the trough of one wave overlaps with the trough of another, we get constructive interference. That produces a bigger crest or a bigger trough. You can see the areas here where we have constructive interference. There's a line of constructive interference right here, another one right here, another one right here. You can see these areas of constructive interference is indicated by the heavier or bigger crests and troughs. In between those areas of constructive interference, we get no wave. Right here you can see calm, right? Area of calm water, another area of calm water, another area of calm water, another area of calm water, and so on. Those are areas of destructive interference. When crest meets trough, they cancel each other out, and we get no wave. If you're on an air mattress, just minding your own business in a pool that has this interference pattern, if you were in position 1, you would bob up and down like crazy because it's big crest, big trough. The waves would be amplified because of the constructive interference. But if you were in position 2 right here, right beside the person in position 1, then you'd be able to lay on your air mattress and read a book and be comfortable because you're not bobbing up and down at all. You have destructive interference. The crests and the troughs have canceled each other out. Now, if this is water waves, like it is in this photo, you can see very clearly where the constructive and destructive interference takes place because we can see water waves. If this is light waves, visible light caused by a laser, we're not going to see the areas of constructive and destructive interference because the laser light has to reflect off of something in order to be observed. You did your lab last week on refraction, trying to find the index of refraction of the glass block. Some of you said in your sources of air for that it would be easier to see the laser beam if there was a smoky or a foggy room. because it would have something to reflect off of. You didn't see the laser beam until it reflected off of the glass block. If you had something to reflect off of, then you would have seen it better. There's nothing to reflect off of in this area right here, so you don't see the laser beam. There's interference taking place. There's lines of constructive and destructive interference, just like there is at the water. You just can't see it because it has nothing to reflect off of. So what we do now is introduce a screen up here. We don't need a screen for interference of water waves because we can see the water waves. But if we want to see the light interference, then we need a screen. What does that screen look like? Well, where there's an area of constructive interference, that produces brighter light. Right? It's big crests and big troughs. It's bright light. So we get a bright spot. And then we get another bright spot right here where we have constructive interference. And then another bright spot right here, and so on and so on and so on. In between those bright spots, we get what we call dark spots, but really what they are is absence of bright spots. We just have no light. So right here, we get a bright spot. Right here, we get nothing. There's no light. Right here, we get a bright spot. Right here, we get no light. Nothing. So it's alternating areas of bright spots, and we'll call them dark spots, for lack of a better term. For water waves, we don't need that because we can see the interference pattern like we can in this photo. If it's light waves, then we need the screen so that we can observe the interference. Does that make sense? There's a graph up on the board right now which represents what we just saw. If we had a screen down here with an area of constructive interference, it would produce a bright spot, and then a dark spot for destructive interference, and then a bright spot for constructive, and a dark spot, and so on. Alternating areas of constructive and destructive interference. Alternating bright spots and dark spots. If we plot a graph of intensity versus position, X position, horizontal position, then you can see in this graph that that central bright spot, or that middle bright spot, is the brightest. It has the highest intensity. Then next to it, we have zero intensity, or very, very close to zero intensity. That's the dark spot, or the absence of a bright spot. And then next to that, we have another bright spot that isn't quite as bright as the first one. And then we have a dark spot, and then we have another bright spot, and so on and so on and so on. So if you ever see a graph of intensity versus position, you know how to interpret this. Bright spot in the middle, because it's high intensity, then dark spot, where it's zero intensity. Then bright spot, where it's high intensity, and so on, and so on, and so on. Now, I want to label this, which basically just shows us what we already have seen. I want to label this in a few different ways. Okay, the first way is to label some numbers corresponding to our maxima and our minima, or in other words, our bright spots and our dark spots. This is the maximum that occurs right in the middle, and then the one that occurs next to it, and then the one that occurs next to it, and so on and so on and so on. And of course, there's the dark spots in between. We're going to call this maximum our central maximum. Our central maximum. Another name for a central maximum would be a central bright spot. Another name for a central maximum or central bright spot would be a central antinode. We don't see that term all that often, but we could. A central maximum, a central bright spot, a central antinode, they all mean the same thing. This next one beside it, on both sides, would be our first order maximum, or our first order bright spot, or our first order antinode. And then we have, beside that, our second order max, or our second order bright spot, or our second order antinode. We're going to assign a number to each one of these. The central is going to be 0, the first order is going to be 1, the second order is going to be 2, and so on. These keep going, not forever. The number of antinodes that you see will be limited by the distance distance is involved and the wavelength of light that you use, but they normally will go beyond 2 maxima. Same pattern applies though. Now in between those maxima are the minima. We will call this one our first order minima. We could also call it our first order dark spot. Or we could also call it our first order node, not antinode, but node. This would also be the first order minimum. And of course, beyond that, we have our second order minimum. And then the second order max, and then the third order min, and then the third order max, and so on and so on and so on. What numbers do you think we're going to apply to the minima here? What number would the first order minimum be? It's in between the central max and the first order max. So what number would we write down here for the first order minimum? 0.5, yeah. And the second order minimum would be between 1 and 2, so we're going to make it 1.5. First order min on the other side, 0.5, and 1.5 on the other side. Now you see two equations up on the board. I want to identify the variables in those two equations by drawing pictures on this diagram. The first one that I want to identify is lambda. That stands for what? Wavelength. Yeah, it's the wavelength of the light. And that's going to be in meters. The wavelength of the light, the EMR that's coming through these two openings. By the way, this same equation, the same argument, everything would apply to water waves or anything else as well. It's just that we don't need to do this so much with the water waves because we can see a little bit more what's happening in between here when it's not light. Okay, so I've identified lambda. That doesn't show up on the diagram because it's the wavelength of the light. Next, I want to identify little d. Appears in both of the equations. Little d is the distance between the two openings, from center of one opening to the center of the other opening. It's going to be measured in meters as well. And the next variable I want to label is L. Sometimes we make this a big L, sometimes we make it a little l. Usually when it's typewritten, like on your data sheet, like on the board up here, it's a little l. I'm going to write it, though, by hand as a big L. The reason I'm going to do that is because if I write that as a little l, it's going to look like a 1 to you. Big L, little l, whatever we end up calling it, it means the same thing. It's the distance from the openings to the screen. And that's going to be measured in meters as well. So far, so good. It's a little confusing sometimes, the difference between D and L, but it's not so bad. This next one is kind of wacky, though. We're going to label X now. X can be this distance right here, the distance between maximum 1 and maximum 2, or it could be this distance right here, the distance from the first order minimum to the second order maximum, or it could be this distance right here, from the second order maximum on one side to the first order maximum on the other side. X can be basically whatever you want, from the distance from one max or min to another max or min. That's going to be measured in meters as well. Now, how is it that 3 people can have 3 different values of X? Okay, let's say Austin has one value of X. Cameron has another value of X. And Benton has another value of X. But yet they all get the right answer, the same right answer. All 3 different numbers They all get the same correct answer. Yeah. Yes, it's related to n. N is the difference in the number for the max or min. It's just a number. No meters, nothing like that, just a number. For this first one, Austin's, we're going from the first max to the second max. We would say for that one, n is equal to 1. 2 minus 1 is 1. For the second one, for Cameron's, I think I use her as an example, we're going from the first order minimum to the second order maximum. You can tell me what n would be in that case. 1.5. 2 minus 0.5. And for the third one, Benton's, we went from the second order max on one side to the first order max on the other side. What's n going to be in that case? Easiest way to do this is subtract, right? 2 minus 1 is 1. 2 minus 0.5 is 1.5. 2 minus negative 1 is 3. N would be 3 in that case. When you're going from one side to the other, make sure one of them is a negative. It doesn't matter whether you go 2 minus negative 1 or 1 minus negative 2. You get n is equal to 3 in both of those cases. So x can be whatever you want, as long as n is consistent with that. Finally, we have one more variable here, and that's theta. Theta is an angle, of course, measured from the central max, always measured from the central, to wherever you want. This could be theta, from the central max to the second order max, or this could be theta, from the central max to the first order minimum. How do we have two different values of theta? Well, if n is consistent with it, we're okay. Angle between the central max and another max or min. What would n be in this case? From the central max to the second order max, we'd say n is equal to 2 minus 0 is 2. What would n be in this case? From the central max to the first order minimum, n would be equal to 0.5 minus 0 is 0.5. Does that make some sense? X and theta, you have some flexibility there. But if you're going to be flexible with it, you have to be consistent with the value of n. If you are, then Austin's answer is going to be the same as Cameron's answer, is going to be the same as Benton's answer, regardless of what numbers they use. You notice in that second equation, so we're going to wrap it up for the day here, there's a big if. The first equation is always valid, just like all the other equations that we do this year. They're always valid, given the right circumstances. But that second equation is an approximation. It's not perfect. It's never perfect. No matter what, it's never perfect. But it's a really, really, really good approximation. In other words, it gives us a really, really good answer. To a few significant digits, perfect. If our angle is small, if theta is small, how big can it get before it becomes a not as good approximation? We usually put that cutoff around 10 degrees. So we say that we're allowed to use the first equation always. We're allowed to use the second equation if theta is less than 10 degrees.